So the first section of this afternoon is by Bernard Carr on black holes, cosmology, and the limits of science. Okay.
Yep. Thank you. First of all, I put a little picture on the right. Don't worry too much about it. I just wanted some image which connected black holes to cosmology, and indeed the limits of science. This is actually a depiction of Lee Smolin's view that a black hole collapses and forms a baby universe, which some people might say was on the limits of science. But I don't want to talk about that in particular. Now, I want to start off referring to Simon's question on the first evening about what we mean by cosmology. And Simon quoted a view, I don't think quoting himself, that it's to do with things on scales bigger than a megaparsec. And I want to start off by saying that that is definitely wrong. You see, you have to make a distinction between cosmography, which deals with the large-scale structure of the universe, and cosmogony, which is to do with the birth of the universe. And they're different topics, but they all come under the heading of cosmology. Now, we learnt, for example, from Joe Silk's talk that you can't actually understand cosmology without understanding what's going on the scale of galaxies and stars and smaller things. So that's one reason why we know that definition is wrong. But more importantly, the one thing we've learnt from cosmology is that you cannot distinguish between macro and microphysics. They are linked at the Big Bang. So if everything else in my talk is wrong, this isn't wrong. Cosmology is actually, in any sensible definition, has got to include everything. It's not just megaparsecs. And furthermore, I'm going to try and get across the idea that what we mean by the universe constantly evolves historically. So it's not only the lower limit, it's also the upper limit of the scale, which is a little bit ambiguous. But then there's also the question of what is science. And the point I'm going to make in my talk is that at the frontiers of physics, which means on the very largest or the smallest scale, you're always, in some sense, on the science-philosophy interface. So there's always been a controversy. And indeed, in the particular context of cosmology, which represents the largest extreme of the scale, there's a border between what I call metacosmology and cosmology. Now, of course, I know Mike's used the same phrase this morning, and we're not necessarily using the phrase in exactly the same sense, although I expect there's an overlap. And furthermore, what I'm going to argue is that this border between cosmology and metacosmology evolves with time, and that what we mean by science also evolves. So it's not only the nature of the universe, it's the nature of science which evolves. And then, of course, there's a link between black holes and cosmology, which is something I'm particularly interested in. Now, actually, Tom himself gave a very nice example of a link between black holes and cosmology in his talk this morning, relating it to holographic cosmology, and it also arose in Bill Unruh's talk. But there's various other problems on the cosmology, metacosmology interface which relate. And indeed, one of the things I want to talk about, if I can get away with it, is the problem of consciousness and the problem of time. Now, I have to say that Simon said I shouldn't do this, but I felt in an embarrassing situation because Simon said that I should go beyond my comfort zone. Well, it's in my comfort zone, but it might not be in Simon's, but anyway. But I am slightly nervous because there are people in this audience who've thought about time much more than me, so I'm half expecting to get shot down. But anyway, I hope it's my one chance to say something about the interface of cosmology and philosophy. Now, I want to start off with this picture to back up this idea about cosmology being the whole universe. This is the famous Ouroboros, which is the snake which swallows its own tail, and around the body of the snake you have all the various scales of structure of the universe with people at the bottom, and then successively larger scales as you go to the right, successively smaller as you go to the left. Now, I have to say that there are many pictures of the Ouroboros. This is my favorite one, and I've taken it from the book by Joel Primack and Nancy Abrams. And I'm saying that because we have to be very careful in these meetings not to show pictures which violates copyright. And Joel and Nancy have promised not to sue me, and I'm very grateful. Anyway, let me just give you a brief 1-minute summary of the history of physics. In some sense, the history of physics is the expansion of our knowledge to larger and smaller scales. And so on the outward journey, of course, that's the journey of astronomy. So we start off with our geocentric view, the heliocentric view, the galactocentric view, obviously as we look to greater and greater scales, a cosmocentric view, and now we have things like the multiverse, which of course are controversial, but remember, anything at the boundary is controversial because it borders on philosophy. And then on the inward journey, of course, we've looked to smaller and smaller scales, so we've got atoms. And the other thing is we discover links between the micro and the macro world. So we discover that the same force which holds the electron around the proton is what determines the structure of solid objects. We discovered nuclei, the weak and the strong forces, which also dictate what goes on in the burning of stars. There's the standard model, the electroweak, and of course now we've got the Higgs. There are also things we haven't yet discovered. We know that supersymmetry may have WIMPs, which may explain the dark matter in galaxies, and then up at the top, again, not experimentally accessible, the grand unified theories. And then right at the top, of course, we've got M theory. Now, to me, this picture is a summary of the triumph of physics in producing an overview of everything in the micro and the macro world. And of course, the crucial thing is that the Big Bang is where it all comes together. Now, why does the Big Bang, if you like, is the culmination of the macro-micro link connection? Why is that? Now, this is just a picture which shows in a light cone structure what happens, the behavior of the light rays. I think there's a point there. As you go back, and you all know this, but the basic point is, of course, that when you look to the larger scales, you're looking back in time when the universe was smaller and smaller, and that is why the head of the snake meets the tail of the snake. So essentially, it simply reflects the fact that the backward light cone converges down at the point there. And the size of the Earth's observable universe is something like 3 times c times the age of the universe. So that's all well understood. But now I want to go back to the question of what actually is science, and in particular, what is physics, which of course is a particular part of science. And what I want to point out is that there is a distinction between, if you like, metaphysics and theology. And I talked about the fact that when you're dealing with the extremes of the very largest and the very smallest scale, you're always dealing with ideas which is sort of people think, well, that's more metaphysics than physics. And in particular, that's true today. But if you can go even further to the level of theology. So let me just take a very particular example. I want to talk about the anthropic tunings. Now, I'm not going to talk about the anthropic tunings per se. I'm going to refer you to a very nice recent paper by Luke Barnes on that, which gives a very nice up-to-date summary of all the anthropic tuning arguments. I just want to talk about the different types of explanation. Now, an explanation which many people would say was a physical explanation, not all people, is the multiverse. I'm sure you're familiar with this idea that if there are lots and lots of universes, some of them are going to have conditions in which the fine-tunings are satisfied. Another explanation was the Wheeler idea that in some sense the universe doesn't exist until consciousness arises. So you have the Big Bang, eventually consciousness arises, which looks back on the Big Bang and brings it into existence, obviously related to the idea of quantum mechanics that consciousness collapsed the wave function. Most people, I think, would classify that as metaphysics rather than physics. But on the other hand, here's a theological explanation. God chose the constants in order that the life could arise. Now, from a logical perspective, I don't think one can argue that any of these explanations is any better than the others. But if you're a physicist, there's no doubt what you prefer. A physicist prefers the multiverse because at least it purports to be physics. And most physicists don't want to introduce consciousness, and they definitely don't want to introduce God. Now, Don did. Don Page mentioned God, but not many people in this meeting are going to talk about God. So the point about it is that from a physicist's perspective, there is a sort of a gradation of sort of antipathy as you go from physics to metaphysics to theology. And that's important sociologically, because if people say that theory is metaphysics, they're less likely to take it seriously or study it. Now, but let's think about this a little bit more. The point is that opinions differ as to what exactly is the boundary between physics and metaphysics. And there are some people, for example, who will say they think the multiverse is metaphysics as well. And Wheeler's ideas would be regarded as theology, and God would be sort of regarded as beyond the pale. And so it depends on your perspective. And then if you wanted to believe, if you took that perspective, well, what's a respectable physical theory? It's the self-creating universe. This is the Hawking's universe in a nutshell. It's not clear how it explains the fine-tuning, but there's no doubt some physicists, that's their favorite picture. No multiverse, no God. But now I want to apply this to cosmology in particular, and I'm going to use this phrase metacosmology in probably a slightly different sense than Tom was using it. I'm using metacosmology to describe an idea which in some sense people think of being on the verges of philosophy rather than physics. It's not quite the same as talking about the philosophical underpinnings of a cosmological theory. And it's not the same as talking about the philosophical aspects of some cosmological theory, which are of great interest in their own right. But it's a metacosmology, would often be thought of as a rather disparaging term. So if you think the multiverse is not physics, you would call it metacosmology. And, but the point I want to make is that the boundary between cosmology and metacosmology is fuzzy, and it evolves. Not everybody will agree, as should be clear from the previous picture. And in fact, the message I want to get across is that historically, that boundary between cosmology and metacosmology evolves. Now, George has introduced this term cosmology with a big C. So as I understand it, cosmology with a big C really covers everything, including theology. I only have a slight criticism of this, George, which is that there's a problem that when you write in English, the first letter always has to be a capital. And so I can't start any sentence about George's theory without starting with cosmology with a big C. So I just use a very big C, George, if that's all right, and use another C. But anyway, that's the point I want to make. Now, there are lots of other examples of metacosmology. People will disagree as to, for example, I'm classifying Boltzmann brains. I'm classifying that as metacosmology. No offense to Sean or anybody. I work on metacosmology too, so I'm not trying to offend people by saying it's metacosmology. Brain cosmology itself, I'm going to come back to brain cosmology. Some people would say, well, that's metacosmology because we've got no evidence for the extra dimension. In fact, it was Joe, I think, who told me about brainless cosmology, which is where you don't make any reference to brains. But then there's the problem of time and consciousness, which is very definitely in the domain of philosophy. But that also involves brains. To me, that's the fundamental problem of consciousness, is the flow of time and the relationship to our brains. But here I'm not talking about the brain in the bottle, I'm talking about the brain in our head. Now, I want to now have a little brief interlude to try and justify this idea that what we mean by respectable cosmology evolves, that there is this transition between cosmology and metacosmology. So I'm just going to give you a very brief history of ideas of the universe. You'll all be familiar with this, so I can do it very quickly. And we obviously started off with the geocentric view, but that sort of died a death when Tycho Brahe observed the supernova Cassiopeia in 1772, and he knew this destroyed the Aristotelian idea that, that the heavens were, the Platonic idea, the Greek idea that the heavens were unchanging and things changed on Earth. Because he knew when he saw that supernova go off, because it didn't change through parallax as the as the Earth went round the sun, he knew that that had to mean something in the heavens was changing. That destroyed, at a blow, the old Greek view that the heavens were unchanging. But nobody believed him. People had their prejudice, and he was very annoyed, and he said, "Crassa ingenia, o coicus, o coeli spectores, o thick wits, o blind watchers of the sky," because people simply wouldn't accept, because they were so wedded to the Greek ideal. Now, I'm going to draw a lesson from each of these slides. This lesson is the theoretical prejudice should not blind one to the evidence. Now, often when I talk about this, I'm talking it in the context of the multiverse debate. And to me, the analog of the evidence is the fine-tuning, because to me, although it's obviously controversial, I regard the fine-tunings as at least indirect evidence for the multiverse. Now, then we have the heliocentric view, but now let's see what Auguste Comte said about this. "We will never be able by any means to study their chemical compositions," he meant the stars. "The field of positive philosophy lies entirely within the solar system, the study of the universe being inaccessible in any possible sense." So he wasn't denying the existence of things outside the solar system. He was just saying it was outside science. But then a few decades later, they get spectroscopy, and he's proved to be wrong. So lesson 2, new observational developments are hard to anticipate. So when people say we can't believe in the multiverse, how do you know? You know, maybe they're going to create a universe at the Large Hadron Collider or in our backyard. Or maybe we're going to go through a wormhole. I mean, you just don't know. You can't always anticipate what science is going to have beyond the horizon. Then we had the galactocentric view. You know, at the beginning of the last century, there was a huge antipathy towards the idea of a universe. It was regarded as metaphysics. And Rutherford said, "Don't let me hear anyone use the word universe in my department." Now, nowadays, people probably say the same thing about the multiverse, but I don't know who the equivalent is. And then, of course, you know there was a great debate in 1921 about whether there was anything beyond the galaxy, the famous debate between Shapley and Curtis. We all know that was resolved very soon after, when Hubble discovered the distance of the Andromeda galaxy, and then he found his famous Hubble's law and the Hubble's constant. And now we know the universe began with a Big Bang. Sorry, this is wrong now. It's 13.8, I guess. But anyway. But then, Friedman, we all, of course, know, he was the person who theoretically anticipated the Big Bang model. He realized it was the solution of Einstein's equations. But of course, no one paid attention to him. Einstein himself wasn't very interested, because remember, in those days, people thought the galaxy was the universe. And so in 1922. So lesson 3, don't reject a theory because it has no observational support. The observational support may come. And here's my favorite character, George Lemaitre, who, of course, we all know now, he had his own Big Bang model independently of Friedman in 1927. He even had, basically, in some sense, Hubble's constant. And then it was translated in English in 1931. And then he proposed the primeval atom in 1932. And so he's now called the father of the Big Bang. But just look at some of the reactions of people. I've just realized I've got a picture of Einstein. Anyway, I'm not supposed to have a picture of Einstein. Anyway, Einstein, your math is correct, but your physics is abominable. Eddington, philosophically, the notion of a beginning of the present order of nature is repugnant to me. He thought it was too theological. He thought it sort of risked bringing in God. Lesson 4, don't be deterred by the opposition of great scientists, because great scientists are often wrong. Either the great scientists will change their mind, or they die out and they're replaced by other great scientists. Of course, history is full of this. And the remarkable thing about the anthropic principle is that really what has made it respectable is the fact that just a few key eminent physicists have started saying it's respectable. So if people like Weinberg and Wilczek and Hawking and Hartle and everybody start saying, I believe this, it has a huge effect. You only need a few scientists to actually sway people. We're pretty sheep-like. And Eddington was, Lemaitre was just amazing, because he not only was the father of the Big Bang, he was also the person who predicted the essentially the future of the universe, because he had the cosmological constant. Even after we had the Big Bang, there was still some skepticism. Alpha and Herman, they did the first calculations of nuclear synthesis in 46. But most people at the time didn't take them seriously. Cosmology was then a skeptically regarded discipline, not worked in by sensible scientists. Lesson 5, be prepared to apply known physics in new domains. Now, admittedly, sometimes one is applying unknown physics in new domains, but it's worth bearing that in mind. Now then, of course, there's the famous discovery of supernova and the acceleration of the universe in 98. And as has been pointed out, most people just assumed until then that the cosmological constant was 0. So ever since Einstein introduced it, but he admitted it was his big mistake, and then after that, everyone made it 0 again, and then that became the big mistake. But the point is, majority opinion is often wrong. Of course, there are people who talked about it, but the majority opinion was that there's no cosmological constant. Then, of course, we discovered the background radiation, and we measured the microwave backgrounds, and you've seen these pictures many times. And so this, of course, not only proved the Big Bang, but also proved particular models to do with the origin of the fluctuations. And for people who work in this area, it really was amazing, because, you know, if you're a theoretical cosmologist, in some sense, part of you must all be wondering whether this is all a game, it's all in your mind. And then when you actually look at the sky and it actually happens as you predicted, I think all the cosmologists will appreciate it. It's an amazing feeling. So, but the key point I want to make is that what makes metacosmology cosmology is data, okay? And it's data-driven. Until there's no data, it's metacosmology. But now we have the data. And now, of course, we've got the BICEP results, which we heard a bit about on the first day. And that's a warning there, too. Don't get too excited by data, because sometimes data goes away. There have been lots of examples of false claims. So new data needs to be confirmed. We all hope this is correct. And some of us went to the mountaintop yesterday to see the telescope where they're going to confirm it. But we have to wait and see. And so now, let's go to the cosmocentric view. And my lesson here is lesson 9. The tide of history may go against the cosmocentric view, by which I mean, historically, the universe has always got bigger and bigger and bigger. At every stage, the conservatives have said, you can't go more than that. Okay, that's not proper science. It's not just a question of whether the universe is bigger, it's whether the application of science can be extended. And actually, George always makes this view about the hubris argument. You know, and George shows this diagram showing how the great hubris involved in extrapolating our model of physics all the way to the horizon, you know, way beyond 10 to the 100 times the horizon. And I agree with George about that. But what I would like to say is that actually the real hubris, I think, is precisely, it's a hubris to assume that the universe does not change. And actually, of course, the multiverse view looks like this. It says that we are just one small part of a little patch of this bubble, which is one of many bubbles. This is the multiverse. Now, I know I'm twisting George's arguments on its head here, but I would say the real hubris is to assume that this little red patch goes on forever. That's what George is criticizing. And I would say the lesson to learn from that criticism is that actually this sort of picture is less hubristic. I mean, I know what George means. He's saying it's hubristic to believe our models. But nevertheless, I think it's an interesting twist on George's argument. Now, but the real question is the universe part of science? And there's been a long debate about this. I've had many debates with George about it. And basically, the question is, George has made, I'm not going to summarize George's arguments. He mentioned them on the first day, and he's quite correct. There has to be some element of testability in science and all this, and at the moment it's not there for the multiverse. But I want to quote what Weinberg said in my book, Universe and Multiverse. We usually mark advances in the history of science by what we learn about nature, but at certain critical moments, the most important thing is what we discover about science itself. These discoveries lead to changes in how we score our work in what we consider to be an acceptable theory. So the nature of science changes. So when people say this isn't science, you're quite right. You've got to say what are the aspects of science which you regard as sacrosanct. But it's not an easy answer to. It's not easy to answer. Lesson 10, the nature of legitimate science changes with time. So is the multiverse really legitimate science? Well, I agree with George that so long as there's no evidence for the multiverse, it is metacosmology and not cosmology. But I only differ because I think in principle there could be evidence for a multiverse. For example, there were the arguments that there was dark flow as though large chunks of the universe were being pulled by something beyond the horizon. This came from Koszynski's work, and he claimed there was this coherent 60 to 1,000 kilometer flow. And in fact, this was even claimed by the Sunday Times as the first hard evidence that other universes exist. Not everybody, of course, agrees with that. This is a picture of the flow showing how we're meant to be being dragged by something beyond the horizon. Even George Sathiou said, such ideas may sound wacky now, just like the Big Bang Theory did 3 generations ago, but then we got evidence and it changed the whole way we think about the universe. And in a sense, that's the message I'm trying to get across. The evidence changes how we think about the universe. And actually, I don't think the evidence for dark flows is very good, but nevertheless, the point is, in principle, there is evidence. And then, of course, there's all the interest in having collisions with other bubbles. There's big literature on that. It goes back all the way to 2006, and again claims there is evidence. Now, for example, there's McHugh et al. They've done very detailed simulations in order to see whether you would see these bubble collisions in the microwave sky. And the point is that there isn't yet any evidence for this, but the point is, in principle, you can look for evidence. So my only disagreement with George is that I agree with him at the moment the multiverse is metacosmology, but I harbour the hope that in principle it can become cosmology. And now let me just say a bit about the changing nature of science. This is the picture I started off with of the Ouroboros. And I've tried to explain that scientific progress involves the expansion of knowledge to ever larger and smaller scales as you go up on the large and the small scale. And I like to think of this as a sort of expanding consciousness. So there's my original Ouroboros, and you can think of the history of science as these little arcs are giving you the range of scales you were aware we had in the 12th century, the 16th century, the 20th century, and the 21st century. And so you see it's remarkable now, our awareness in some sense has almost expanded to the largest and the smallest scales. And now the question I've emphasized is that the nature of science changes as it progresses and addresses new questions. The micro and the macro frontiers have always been on the border of physics and metaphysics. That's why I kept quoting all these people who were skeptical. But what is actually rather interesting now is that actually the macro and the micro frontiers have merged. Remember, we more or less got to the top of the Ouroboros. And the question is, does that mean we've reached the end of science? Or is it the transformation of science? And we don't know. I mean, there are some questions which are going to be beyond science. There's no doubt about that. And certainly some of those questions in the theology side, for example. I have a hunch this is not the end of science, but that it's actually a transformation in the nature of science, another paradigm shift. Now, I want to now get on to another topic. I'm only going to deal with this very briefly, which is to do with black holes. Now, we all know about black holes in the Schwarzschild radius, and we know, of course, there are the stellar black holes, and there's the intermediate mass black holes and the supermassive black holes. The overwhelming evidence for stellar black holes, this is Cygnus X1. This is an observation of a black hole being born, actually, in 2010. I forget the number of the galaxy. Overwhelming evidence, I would say, for supermassive black holes in AGN. Joe Silk talked about this. Our Milky Way is 4 times 10 to the 6. Quasars are powered by 10 to the 8. Do you know, I only learned this a few months ago, the biggest black hole in a galaxy now is 20 billion solar masses. It's half the mass of the bulge. And there's this famous diagram, of course, you know, between the mass of the bulge and the mass of the black hole. There's no doubt about that. I have to say the evidence for intermediate mass black holes is a little bit more tentative. But it may be the first stars were like that. But of course, what really interests me is the primordial black holes. Some of you may know I've devoted half my life, or more, to working on primordial black holes. These are the black holes that form in the early universe. The key point, of course, is that in order to make a small black hole, you have to have you need a high density, because the density goes like m to the minus 2. But in the Big Bang, the density goes like 1 over time squared, so it goes up arbitrarily high, so you get arbitrarily small black holes. And primordial black holes, therefore, simply have a mass which is the black hole horizon scale. And that goes all the way from 10 to the minus 5 grams, 10 to the 15 grams, that's for black holes that form at the Planck time. At 10 to the minus 23 seconds, it's 10 to the 15 grams. But you can also get macroscopic objects. At the quark-hadron phase transition, you form solar mass black holes, and at 1 second, you have 10 to the 5th solar mass black holes. So primordial black holes are pretty interesting. And of course, they also evaporate. We heard from Bob Wool this morning about that. They have a temperature and a lifetime, and they may explode today. But the crucial thing is this is only important for primordial black holes. Now, we know, of course, that that is an incredibly important result, because it unified quantum mechanics, thermodynamics, and relativity. But the point is, we don't actually know that primordial black holes exist. There's no evidence at all that they exist. And yet, only by thinking about them, because I was doing my PhD with Stephen when he came up with the result, it was only because he was thinking about primordial black holes that he came up with this result. And I think this tells you something interesting, that something can be interesting even if it's not really there. This thinking about primordial black holes was tremendously important. It doesn't matter from that point whether they existed. And I think that's true of many things in physics. Even if string theory is wrong, I bet you it's been useful to think about it. Now, I want to go back to this diagram, because you might say, well, how does this link with cosmology? I want to now populate this diagram with black holes, all the black holes that exist in nature, because I'm pretty obsessed with black holes. And so Planck mass black hole, 10 to 15 gram black hole, lunar black holes, these two could in principle have the dark mass. Stellar black holes, intermediate mass black holes, the Milky Way black hole, quasar black holes, even in some sense the whole universe is a black hole. Now, if you believe in extra dimensions, it may well be that in fact you can, the Planck mass the black hole mass is bigger, and then you can generate these things in the accelerator. But I love this diagram because it shows that black holes actually play a crucial role in linking the macrophysics and the microphysics. And most people who work on black holes focus on a particular type of black holes. But really, the domain of black hole physics is much more extensive than that. Now, what's the link between black holes and cosmology? Well, Tom Banks gave a nice example. Actually, I had lots of things I could have talked about. The birth of the universe, Smolin had this idea that when a black hole forms, it gives rise to a baby universe, which mutates the constants. I'm not going to talk about that, but I did show his picture on the front of my beginning of my talk. I'm going to talk about a link between brane cosmology and the flow of time via 5-dimensional Schwarzschild de Sitter solution. Other things I could have talked about but won't. I'm interested in the question of whether if you have a cyclic model, can the black holes which formed in the last cycle, the collapsing phase of the last universe, survive and persist through to this phase? So if it were true, you would have a direct signature of what happened in the previous cycle of the universe. So I've spent 30 years thinking about the black holes that formed in the first second of this universe, and I'll probably spend the rest of my career thinking about what happened to the black holes that formed in the last second of the previous one. And then what I'm particularly interested in at the moment, but I just decided I don't have time to talk about it, is what I call the black hole uncertainty principle correspondence, which says that if you look at the generalized uncertainty principle, it suggests that there is a very intimate link between black holes and the uncertainty principle. In fact, I'm not going to talk about this. There's a series of papers, in particular, in connection with loop black holes. It seems to me a beautiful idea, which is very little explored, which simply says that if you take the generalized uncertainty principle, it suggests that the Compton wavelength sort of naturally turns into the black hole radius, which says there is this conceptual link between black holes and the uncertainty principle. But I just want to focus in my last few minutes on this one, brain cosmology, because I wanted to talk about the last one because there's some great experts in the audience on quantum gravity, but I decided I wanted to talk about this more philosophical one about the nature of time. Now, this is where I might get into trouble. Now, there have been some great books about time recently, and here are 3 books. Now, Sean has promised me he's not going to sue me if I show the cover of his book. These are all, they're different, take completely different views about time. There's lots to agree about and disagree about, but they're all great books. But there's one point I want to make about these books. They barely mention consciousness. And by and large, physicists don't like to mention consciousness. But to me, consciousness is the fundamental problem of time. So I'm sort of frustrated about that. And so I want to say something about consciousness and the flow of time. Now, I know the philosophers here understand these things much more deeply than I do, but this is just a well-known problem in relativity. Consciousness does not, you cannot in terms of relativity describe the flow of time. So if this is my world line in my brain, naively I think of my consciousness as sort of like a bead going along the wire. And I also naively think that I make a choice as to whether to carry on giving this talk or to leave. But we know that is how we experience the world, but we know, according to relativity, it can't be like that, because in Einstein's block universe, there is no flow of time. And here are some famous quotes. Weil, the objective world is, it does not happen. Only to the gaze of my consciousness crawling upwards along the lifeline of my body does a section of this world come to life as a fleeting image in space which changes in time. Einstein himself, when his friend Michel Bissos died, now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubborn, persistent illusion. So physicists know this, and of course, people have argued about how you solve this problem for a long time. But I want to remind you of a particular approach which a philosopher called C.D. Broad pushed. And he said, to describe the flow of time, there's no doubt about it that to describe the flow of time, or consciousness, you have to go outside of four-dimensional description. But I'm going into the domain of philosophy. But anyway, he was an eminent philosopher. He said, well, I can describe the flow of time if I have an extra dimension. So this, if you like, is relativity. So there's my world line, and then I may make a decision. That's another bit, and then I make another decision. There's another bit. So in some sense, this extra time is, if you like, this extra dimension is like a second time, which describes mental processes. So it's a sort of five-dimensional picture. Now, I like this picture. Now, I'm sure that I don't know how Dave and the philosophers are going to react, but anyway, this is a picture that was at one time popular. Now, why I like this is because I'm interested in brain cosmology. And actually, in brain cosmology, you can think of the brain as moving through this five-dimensional bulk. And if you take that, and remember, the brain cosmology is respectable, at least if you're a cosmologist. It's in METACOSMOLOGY, but it's still, you can still write papers about it. But this picture, you just turn it on its side, and it's exactly the same as this. So I'm suggesting that there is a link between the flow of time and this extra dimension in brain cosmology. It doesn't solve the problem completely. You have to focus on some concept of specious present, but I don't have time to go into that. And just to make it clear, that, and George has spoken a lot about this, and he's emphasized the fact that you need an evolving block universe. And I agree with George, absolutely. These are the different sorts of futures in dotted lines, and you sort of solidify. George does not agree with me about needing a fifth dimension, but at least that's what I'm doing. Now, just for the people who are the relativists, to say this isn't just pure waffle. In brain cosmology, what happens is you think of the brain as moving through the fifth dimension in a static bulk, and the solution is the 5D Schwarzschild anti-de Sitter solution, which looks like that. And so essentially, in that solution, you have the mass of a black hole, a five-dimensional black hole. You have a cosmological constant. And the fifth dimension is sort of associated with the scale factor. The people who know about this don't really need to have it explained. But anyway, this is what the solution is. And the solution has the feature that you actually, the main point I'm making is that you describe the motion of this brain through this 5-dimensional black hole solution. And in some sense, the universe emerges from a black hole, a 5-dimensional black hole in this picture. And I'm just putting that in to show that it does actually link with the idea of black holes. So anyway, what I'm saying is, now also Simon said, whatever you do, don't mention consciousness. So I'm sorry, Simon, but to me, consciousness and time really go together. The real problem of time is the problem of consciousness. So to me, it's a question, is mind fundamental or an incidental feature of the universe? Now, because of my interest in things, the anthropic principle, quantum theory, the flow of time, I actually think it's fundamental. And of course, lots of other physicists have said this. We had a beautiful talk on Saturday evening about, sorry, I've forgotten. Thank you. Yes, thank you. Yeah. About how many physicists. I mean, obviously, quite a lot of physicists accept that consciousness has to come into physics, but they're still a minority. And so I just want to ask the question. We know about these two approaches to physics, quantum theory and relativity theory. And the whole question is the final theory going to be more like relativity theory or more like quantum theory? I harbor a hope that the final theory, whatever it is, will in some sense accommodate consciousness and first personhood. And that became a rather heretical concept, but I was really pleased when Jim Hartle is talking about first personhood. And quite a lot of other people are beginning to talk about this. So I hope I'm not going to be burnt at the stake for making these suggestions, but I personally do think that my experience of the world, consciousness is fundamental, and I think we should be extending physics as far as possible to accommodate our experience. So I think consciousness should be a part of physics, and one should no longer be just brushing it off under the carpet and saying, no, that's metaphysics. So thank you.
Now just on time. Okay, so comments, questions? Okay, let's start by Joe.
Thanks. That was a beautiful talk, Bernard. So you mentioned 3 possible views of fine-tuning, but I think you left out a 4th, which is very important, and it's the inverse of something you mentioned. Let us not be blind to new observations. Well, let us also not be blind to the possibility of new theories. So I think one very acceptable view is that, as in the time of Kepler, when he invented something rather weird to explain the fine-tuning of the planetary positions, we should perhaps think that someday we may have a better theory, improvement on string theory or whatever, that would be an alternative to the multiverse and give us a fine-tuning experience.
Yes, thank you, Joe. And in fact, there are 2 examples I can give straight away, which I didn't mention. One is, of course, Smolin's own view, because Smolin's idea of black holes giving birth to universes was proposed as an alternative. But that is a multiverse, of course, but it's not the multiverse in the same sense. In Smolin's picture, most of the universes are populated, whereas in the normal multiverse picture, only a tiny fraction. And of course, the other view is Paul Davies's view, which says that in some sense the laws of nature evolve so as to make life arise. So I completely agree. There are other views other than the multiverse. I agree. And I just didn't have time to mention that. But I'm just expressing my personal prejudice. I'm quite fond of the multiverse.
Thank you so much for that talk, Bernard. Cormac O'Rafferty from Ireland. I really like your theme that a lesson of history is at the border between what we call physics and what we call philosophy, and in particular in the case of what we call cosmology and what we call metacosmology evolves. And I'd even go so far as to say that, particularly at meetings like this, it does strike me that we don't always have as much cognizance of history as we should, because it's very, very helpful. But I would say that there's a caveat that. I mean, you go on to say things like, so that today's metacosmology becomes tomorrow's cosmology.
Could do.
Oh, yeah, but it could do, exactly. But it doesn't say could do here, and it's important. You know, there's plenty of examples from history where that didn't happen. In fact, you know, in the language of Lakatos, it went off into programs that were not helpful at all. And just at one specific example of that, it puzzles me that so many people at the frontier, like you often use the word Big Bang when you're clearly talking about a theory of origins, you know, as if it's a done deal. And even the picture up there would in many ways, to me, suggest that. Was, you know, I would have thought many of the historical people you quoted and many of today's researchers would say, well, hang on a minute, you know, when we talk about the Big Bang, we're talking about something that was once very small and very hot and very dense, full stop. You know, we don't mean anything else, you know, whereas several times in your talk, I got this distinct feeling you were talking about an actual theory of origins.
Well, I mean, the point about the multiverse is that one of the arguments for the multiverse is we want to explain, I mean, we don't want to believe the universe began with a Big Bang, we don't want to invoke God, so we want to say that there was something in physics which allowed us to describe the creation of the universe. But in that case, if there is some meta-theory of physics which allows us to describe the creation of the universe, it must describe the creation of other universes as well. So I don't know what that theory is, but certainly there is an underlying assumption that that's one of the arguments for the multiverse, that if you have a mechanism for creating one universe, it is going to create other universes. What the actual nature of that Big Bang is, I mean, obviously, I'm just meaning there is a condensed state. Personally, I like cyclic models. I quite like the idea that there was a preceding collapse model. But that's my personal view. And your first point was about the... Yes, about the fact that some metacosmology things are wrong. Absolutely, and I'm not claiming that everything in metacosmology becomes cosmology. I have my own... Remember, metacosmology is a whole bundle of ideas. It involves things like Boltzmann's brains as well. Now, I have a personal hunch that multiverse will end up being in cosmology. I don't actually think Boltzmann brains will ever end up in cosmology. I could be wrong.
I'm Sven from Copenhagen, and you were telling in this classification of black holes after their mass that in some measure we can consider our entire universe as being inside a black hole. And I just had an exchange with Jean Carroll, and he disagrees strongly with this because the singularity is placed wrongly relative to and so on. Do you have a little comment on this?
Let me qualify what I meant by saying the whole universe is a black hole. It's a very loose statement. I mean, a black hole, if you define a black hole as something whose radius is 2gm over c squared, there is a certain sense in which the universe is a black hole. But obviously, a black hole is defined in asymptotically flat space. So it's not a black hole in that sense. In fact, it's more like a white hole. However, the reason I said it's more like a black hole was referring to my remark at the end about the five-dimensional Schwarzschild anti de Sitter black hole. So in that particular model in brain cosmology, you can think of the origin of the universe as a five-dimensional black hole. And so I think in that context, Sean is probably not disagreeing with me, though he can perhaps comment for himself. So I was actually making a slightly more sophisticated point, maybe just as incredible, because not everybody believes in five-dimensional black holes. And of course, the key point I wanted to make about the top of that Ouroboros is that what's to me of great interest at the top of the Ouroboros is that that's where the extra dimensions come in. So if you were to ask me, what will the new features of this science, if there is going to be a transformation of science as opposed to the end of science, what will the features be? And I would say extra dimensions and consciousness. Now, of course, extra dimensions is not very popular either in some courses, but nevertheless, I'm just revealing my prejudice.
Okay, so we have a lot of questions. I think we have Jana, George, and Tom. So we'll take 5 more minutes if is the organizer okay? Okay, so you will have the end. Okay.
I have a simple, or it's not a simple question, actually, a quick question. In brain world cosmologies, I've always been curious how one envisions that the brain is going to land there. And sometimes in a special place in the bulk, for instance, in Randall syndrome, it really has to be at a particular location. So in a Big Bang model, how are you imagining it gets there? It's so big and flat, it's so smooth, those kinds of situations.
Yeah, I mean, what happens in Randall syndrome's picture, in this solution here, that's a very special solution in which the mass is 0, and so this scale factor, the A, which is the scale factor of the universe, sorry, it's called big R, is constant. So Randall syndrome itself is a very special case where the brain doesn't move at all. This is a generalization of that in which you introduce the black hole mass. Now, the way this actually happens is that you can think of this scale factor R, that's simply the cosmic scale factor. And literally, the way you think of this, you can think of this brain as moving, but actually, at sufficiently early times, it essentially comes out there is a black hole event horizon, a 5-dimensional black hole event horizon. And so the universe, in some sense, starts off in a 5-dimensional black hole, and then it becomes an ordinary, our normal universe. And I was puzzled by that because I used to speak to some of the brain cosmologists who don't talk about it too much. And I said, well, isn't that interesting? And there is a sort of debate about whether you believe these solutions when they're inside the black hole because the space and the time coordinate change. So funny things really happen. But as far as I can see, this is a genuine interpretation of brain cosmology. But of course, most brain cosmologists do not link this with the philosophical problem of the flow of time. But I don't see why not, because it's exactly the same picture. But, but no one would want to put consciousness into physics. So obviously not many brain cosmologists who want to put consciousness into brain cosmology. Why not?
Bernard, your talk has raised in my mind the following. I'm going to be controversial now for once. Let's think now, we're going to put together our funding application for 100 years from now. Now, what are we going to be doing as cosmologists? Now, by that time, all of these things will have been done. We will have sorted out BICEP, we will have seen everything which can be seen by big telescopes 100 years from now. So what will cosmologists do at that time? Will they now say cosmology is a finished subject and that is the end of it? Or will they say something like, we've done what physical cosmology can do in terms of seeing by telescopes at every wavelength imaginable. We've even had gravitational wave detectors doing everything. And will they then turn and say, actually, we also get evidence about the nature of cosmology by looking at our own experience as human beings who live in the cosmos, and therefore what we experience is evidence about the nature of the cosmos. And there could be that there's going to be a transition taking place at that time once we have got, in effect, all of the data we are ever going to be able to get about the cosmos from observations with telescopes. I'm not saying that is necessarily the case, but I'm saying we will at some point run up against a boundary like this.
I completely agree, George, that eventually we will come to the end of our journey. I mean, it would be nice to think the journey goes on and on forever, but at some stage, and after all, if we have a dream of a final theory, we will have a final theory. Of course, the time scale, I bet it's not on 100 years, but eventually there may be physics, if you like, might come to an end. There will still, of course, be the whole, most of us don't work on fundamental physics anyway. There's the whole domain of the mesoscopic, of complexity and things, which will keep us going. But fundamental physics may well come to an end. But then that's why it's so crucial. What is the nature of, has science, have we already reached that point when we get to the top of that Ouroboros? Have we already come to the end? And I don't think we have, but some people might argue we have. And then you're saying, well, how will nature transform? How will science and physics transform at that point? I suspect that even the nature of cosmology will change in a rather fundamental way, because in response to Simon's initial remark last Friday, I was saying that I actually think cosmology is everything, not just the big, not just the small. It really is everything, because the whole point about cosmology is that everything is linked. And I must confess, although this is going to get me into trouble too, when I say everything is linked, I mean my experience. I mean first-person consciousness things as well. So I think that also has to be part. Now, so I don't think there is this clear link between, at the moment, obviously, consciousness has nothing to do with cosmology. It is not inconceivable to me that there will be a level of cosmology which will bring in the first person. And indeed, Jim Hartle even talked about that in his presentation. So, sure, on a 100-year timescale, the world will be very different. And you're basically asking what happens when science comes to an end, or physics comes to an end. And I would say, well, you're making a distinction between fundamental physics and the rest of it. I suspect normal physics will carry on for a long, long time after fundamental physics is finished.
Yeah, I'd like to sort of make more distinct what I meant by metacosmology. and why I think your historical analogies may be misleading in this context. So in the the string landscape multiverse and eternal inflation, and even in my own model, there are many things about the multiverse which will never, in principle, be measurable. Just in principle, according to the theory. That's different than saying, oh, it's so hard to measure these things, they're so far away, we shouldn't pay any attention to them. It's the theory itself says it's impossible to measure these things. And then you come to the question of the degree to which this is science. And what I think is, that's why I prefer to use the word meta for it, because I believe that some pieces of it may be testable, like we might see bubble collisions on the sky or something like that, but we will probably not test enough of it that we can scientifically say, yes, indeed, there really is an explanation for why the cosmological constant is what it is, because there are 10 to the 500 different possibilities for what it was. That we will just never, ever, in principle, according to the theory, see enough evidence that this is the right explanation of that point.
But the question,
because of that, it's not the same as what I consider science, and I should stop.
I agree, but on the other hand, the question is how much evidence do you need? Because the point is, there's lots of examples of physics where you can't confirm every aspect. You can never see a free quark, you can never see a black hole. So one doesn't normally demand that every aspect of a theory be actually verifiable by observation. So you may be being too hard on yourself, because your model may still be, somebody might say, well, I'm going to believe Tom's model because certain predictions, certain features of it are confirmed. I mean, if you're saying every feature has to be confirmed, then you're right. But that's precisely why the cosmology, metacosmology interface is fuzzy.
So we have
Sorry.
Yes, we have to stop the questions, even though there are still more. And now we have Daniel Sudarski, who will tell us about quantum origin of fluctuations. Thank you.